Welcome to videos on data converters. So in this video we shall see analog to digital converter. So this is part 1. So let us see the basics of ADC. An ADC provides inverse function of a DAC. It accepts the analog input Vi and produces an equivalent output B1, B2, B3 up to Bn, which is a digital output. As we can see here, an ADC, as the name itself indicates, it is analog to digital converter. It accepts the analog input and gives the digital output. So the digital output we will get is B1 to power minus 1 plus B2 to power minus 2 till Bn bit, which is proportional to the input voltage divided by the reference voltage. So K into reference, which is nothing but V into the FSR, full scale range voltage. It is input voltage divided by the full scale range voltage. Now this is a block diagram of an ADC. This is the block diagram of ADC where the input given is analog and we have the output, digital output, which is B1 to Bn. An ADC includes 2 additional control pins. So it is surprising to see there are 2 more different additional pins here. One is start input to tell the ADC when to start the conversion. So as soon as it gives the input voltage, the ADC will not give the equivalent binary output or the digital output. We should say when the ADC should start the conversion. So that should be given from this start pin, which is an input pin. So this is required to tell the ADC when to start the conversion operation. Next is EOC. So as the name itself indicates, EOC stands for end of conversion. So end of conversion is an output pin to announce when the conversion is complete. So this is a start pin. It will say ADC when to start the conversion. Now once the conversion is done, the ADC gives an output voltage, which is EOC, known as end of conversion. It's an output pin to announce when the conversion is complete. So this, whenever EOC becomes high, this indicates that the ADC has converted the input voltage to digital form. So these are the 2 extra pins as compared to your DAC. So this is the transfer characteristics of an ADC. So when we say transfer characteristics, we want to have the x-axis as the input voltage. So this is Vin, and the y-axis is the output or digital value. So here we have considered an example of a 3-bit ADC where the output is 3-bit B1, B2, B3, and we can see we have the analog voltages which is 0. The maximum voltage VFSR is equal to 1 volt, and we can have 8 different possible inputs. One is 0, other is 1 by 8, 2 by 8, 3 by 8 up to 7 by 8. Let us try to understand how does the conversion happens. So VFSR, in this particular case, we are considered as 1 volt, that is voltage full scale range happens to be 1 volt, and 1 LSB, as we know in the previous case of DAC also, 1 LSB is nothing but VFSR divided by 2 power n. In this case, n is equal to 3 now, so VFSR happens to be 1 volt divided by 2 power 3, that is 8. So that's why, okay, as you can see here, so 1 LSB happens to be the voltage from here to here. So that's why 1 LSB is actually 1 by 8 in this particular case. So similarly, we can define half LSB. Half LSB is nothing but half of this VFSR divided by 2 power n, which happens to be VFSR divided by 2 power n plus 1. So half LSB happens to be, in this particular case, 1 by 16, because n is equal to 3. So VFSR is equal to 1. So 1 by 2 power 4 happens to be 1 by 16. So this is the basic definitions of VFSR, 1 LSB, half LSB, all those things. We'll get to know in the future slides why this half LSB is important in case of ADCs. Now you can see we define something like quantization error. So as you can see here, VFSR is equal to 1 volt. The conversion process partitions the analog input voltage into 2 power n intervals. As it was said earlier, we are dividing the input voltage from 0 to 1 volt in terms of to 2 power n intervals. So 2 power n intervals means 8 intervals. So this is 0 to 1 by 8, 1 by 8 to 2 by 8, 2 by 8 to 3 by 8. So likewise we have 8 equal intervals, and all the values of Vn within the given range are represented here. So from 0 to 1 volt, we are dividing that into 8 equal parts, and we are writing it as, so 8 equal intervals, it is 1 by 8, 2 by 8, 3 by 8, so on so. Now, for example, code 011. So we have a code 011 corresponds to the mid-range value, that is 3 by 8. So mid-range value happens to be, now you can see it is 3 by 8. So 011 corresponds to 3 by 8. Actually represents all the inputs within a range of 3 by 8 plus or minus 1 by 16. As you can see here, when the input voltage is 3 by 8, the output is 011. Carefully observe here, when the input voltage is 3 by 8, see the corresponding output voltage. The corresponding output voltage is 011. See, when the input voltage is plus or minus 1 by 16th of that 3 by 8, if the input voltage is this 3 by 8 minus 1 by 16, then also the output code is 011. When the input voltage is 3 by 8 plus 1 by 16, then also the output voltage is 011. Meaning to say, for example, code 011 corresponds to the mid-range value Vi is equal to 3 by 8, actually represents all inputs within the range of 3 by 8 plus or minus 1 by 16. Any voltage which is lying at 3 by 8 plus or minus 1 by 16th of this will be represented by 011 only. Now you can see the DAC is unable to distinguish any voltages which is here and here. So anything around 3 by 8 up to a range of 1 by 16, the input cannot, so the ADC cannot differentiate between 3 by 8 and 3 by 8 plus 16 and 3 by 8 minus 16. Now here you can see, due to the inability by the ADC to distinguish among different values within this range, the output code can be in the error by as much as half LSB. So we know that 1 by 16 happens to be half LSB. Now you can see we were supposed to represent 3 by 8 as 011, that is fine. If the input voltage is 3 by 8 plus of half LSB, the representation would have been slightly more than this. Now because the input voltage is more here, but we are still representing it by 011 code. Now we can see there is an error of half LSB plus half LSB. So when you consider this, okay, this is actually the code would have been slightly more than that. Now you can see the error is actually minus half LSB. When you want to represent 3 by 8 minus 1 by 16, the representation would have been slightly less than 011. Since we don't have any bit which is less than 011 and 010, in between that we don't have any bit. Now we'll be making an error of plus half LSB at exactly 3 by 8 minus of 1 by 16. So due to the inability by the ADC to distinguish among different values within this range, the output code can be in the error as much as plus or minus half LSB. So that's what you can see here. This EQ actually represents the error, the representation error. So let us consider this input voltage as 0 and output is exactly 0, 0, 0. So there is no error here. Now the input is 1 by 16. When the input is 1 by 16, we are still representing the code by the output by 0, 0, 0. Meaning that, so there is an error occurred here. So what is the maximum error that is at 1 by 16? The maximum error at 1 by 16 is minus half LSB. So we were supposed to represent it by a higher bit, since it is not being represented. So that's why there is a minus half LSB error over here. Now you take that same 1 by 16 or slightly more than that. Now you just consider a voltage which is here. Now that input voltage will be represented by 011. So actually this is not exactly equal to 011, but you are still representing it by 011. 011 actually corresponds to 1 by 8. So for 1 by 8 representation, for 1 by 8 input voltage, if the representation is 0, 0, 1, then there is no error. For an input voltage which is less than 1 by 8, if you are representing it by 0, 0, 1, so then there is an error. What is the maximum error you will be making? The maximum error of half LSB will be done if the input voltage is 1 by 16th of uh, 1 by 16th of this value. Okay, assume that in the same case, if the input voltage is 1 by 8 plus of 1 by 16, so we are actually making an error. We are still representing the output voltage by 0, 1, 1. So which would have represented by a greater value. Since we don't have any value between 0, 0, 1 and 0, 1, 0, we are still representing 1 by 8 plus 1 by 16 as 0, 0, 1. So there is an error of minus half LSB done for 1 by 8 plus of 1 by 16. Meaning to say, if at all, if the input is exactly 1 by 8, the amount of error is 0. If it is 1 by 8 plus 1 by 16, the error is minus half LSB. If it is 1 by 8 minus 1 by 16, then the error is plus half LSB. You take this for any case. So you take the case of this 6 by 8. So 6 by 8, if the input voltage is 6 by 8, then there is no error. If it is 6 by 8 plus of 1 by 16, you can see there is an error of minus half LSB. And if it is 6 by 8 minus of 1 by 16, so there is an error of plus half LSB. So this way, so there is an error happening for representation of any bit other than 1 by 8, 2 by 8, 3 by 8. So this we call it as quantization error. This uncertainty is called as quantization error, also quantization noise, which is called as EQ, is an inherent limitation of any digitization process, because when it is a digitization process, you cannot have every analog input voltage being represented by its equivalent bit. So we're going to have some quantization error, meaning we're going to fix, okay, for 0, 0, 0, I'm having input voltage of 0. For representation of 0, 0, 1, the input voltage should be 1 by 8. If the input voltage lies between 0 and 1 by 8, so we are making a demarcation that till 1 by 16 you represent it as 0, 0, 0. Anything more than 1 by 16 and less than 1 by 8 you represent it by 0, 0, 1. So we are making an error of plus half LSB at exactly 1 by 16. That error is going to reduce to 0 when you are representing 1 by 8. When you are representing again 1 by 8 plus 1 by 16, you are making an error of minus half LSB. So this is what is called as quantization error. This exactly looks like a sawtooth waveform. Now we shall again see this quantization error. Quantization error is like a sawtooth waveform. So its peak value is half LSB. As you can see here, this is half LSB. So we know that LSB is given by VFSR divided by 2 power n. So half LSB can be written as VFSR divided by 2 power n plus 1. And since it's a sawtooth waveform, the RMS of a sawtooth waveform will be equal to peak voltage divided by root 2. So peak voltage here in this case of, now we know that for a sine waveform, the RMS voltage is the peak by root 2, whereas for a sawtooth waveform, the RMS voltage is given by the peak voltage divided by root 3. So peak voltage is half LSB, so half LSB by root 3 happens to be the RMS value. So half LSB can be written as FSR divided by 2 power n plus 1. So divided by root 3 happens to be the RMS value. So this is what is EQ now is equal to, upon substituting this root 3 is there, 2 is there. So we can write this EQ, that is the RMS value of that quantization error can be written as VFSR divided by 2 power n root of 12. Now this way we can understand the basics of the ADC, where we have a quantization error for each and every bit. The maximum error would be half LSB, the minimum error is minus half LSB.